Greetings. In this video, we'll be talking about binomial probability distributions. So binomial probability distributions are a particular type of discrete random variable distributions. So what that means is, remember, discrete says that there are a finite number of possibilities that the random of values that the random variable can take on. So that's certainly going to be the case in binomial probability distributions. I also want to remind you that in a probability distribution, what we're looking for is a list of all the possible values for our random variable, along with the probabilities for each of those values. And so ultimately, this is like what we'd like to be able to create for a binomial probability. All right, so underneath every binomial probability distribution is a binomial probability experiment. And so our first task is to be able to recognize a binomial probability experiment. So first of all, a binomial probability experiment is made up of trials. And each trial has two disjoint possible outcomes. So by disjoint, I mean that they are not overlapping or mutually exclusive. So these outcomes, the two different outcomes, there's either one happens or the other. They can't happen together. We often call these, the two possible outcomes, success and failure. But don't read too much into this naming. Sometimes it's arbitrary what you would call a success and what you would call a failure. So there are these underlying trials. We're going to have a fixed number of trials that kind of build our experiment. Let's see. Each trial is independent. And then lastly, the probability of success is the same for every trial. So let me give you an example. This is one that's commonly used both in just the discussions of probability in general and then certainly for binomial probability distributions. Let's say that our binomial probability experiment is to flip a coin 3 times, and we're going to count the number of heads. I'm just using a capital H there as a shorthand for heads. So, all right, let's see if we meet the conditions here. Each trial has 2 possible outcomes. Well, when you flip a coin, the possibilities are that we would have heads or tails. Now, of course, we could call one of these a success and one of these a failure. So maybe if we're going to count the number of heads, then it looks like those are our successes. So we have a fixed number of trials. Well, we're going to do this 3 times, so that's 3. Each trial is independent. When you are flipping a coin, it really doesn't matter what's happened on previous coin tosses. Every time you start fresh, you flip the coin, what is going to happen does not depend on what's happened in the past. So we're good to go on independence. And the probability of success is the same for every trial. Each time that we flip a coin, the probability of success is 1/2. And even if you were to flip the coin hundreds of times and not just 3, and maybe you would have observed tail after tail after tail. You may think that this the probability on the next coin toss, the probability for heads is higher, but it is in fact still 0.5 or 1/2. So I think that we meet all the conditions of a binomial probability experiment. And in this case, I think we can actually construct the probability distribution in a table. So the possibilities, if I'm counting the number of heads in 3 coin tosses, I could have 0. So that would mean that you had all tails, 1, 2, or 3. And now I want to assign a probability to each of these. So in a previous video, I discussed the strategy of tree diagrams, and I'm going to use that strategy here. When you flip a coin one time, the possibilities are heads or tails. And let's say that you were to get heads on the first coin toss, and you were to flip the coin another time. You reset, and again have 2 possibilities, heads or tails. Maybe you get heads on the second coin toss. On the third coin toss, again, you have 2 possibilities. Now, as far as the different paths that I could take, there are a total of 8. You could have heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. So the last one corresponds to this last path of all 3, just like the first one corresponds to the first. So there are 8 paths here, but now I'm interested in counting the number of heads. So this sequence, HHH, that's 3 heads. HHT is 2. This is 2. This is 1, 2, 1, 1. And then this is 0. Now, of these 8 sequences, how many involve 0 H's? That's 1 out of 8. This is 3 out of 8, 3 out of 8, and 1 out of 8. Now, if this is a valid probability distribution, these should add up to 1. And indeed they do. 1/8 plus 3/8 is 4/8, plus another 3/8 is 7/8, and that's 8/8 or 1. So this is a valid probability distribution. In fact, this is a binomial probability distribution. All right, so let's say that we want to, actually I'm going to hold off to our next video, and I'm going to show you how you can calculate these probabilities more generally using your calculator. So I hope you'll join me for the follow-up video.